Classmates, good morning, good evening, good afternoon. My presentation will be on the machine learning method called the Gaussian process. Okay, before we get into Gaussian process regression, we have to have a brief overview of a normal distribution. As machine learning and data science students, I think it's necessary that we internalize these ideas and not just memorize these key concepts. And a part of internalizing these concepts is repetition of review. So here we have a normal distribution. This is the distribution of the students' grades in Dr. Mike's class. So here is our function. The normal distribution is a function of the mean and the standard deviation. Those are the parameters of our distribution. So Gaussian process regression, we have a prior distribution, right? And our prior distribution is basically based on the knowledge we have, what are our beliefs of the probabilities? So um, normally this is the distribution of the students' grades in Dr. Mike's class. Now, the posterior distribution is whenever we observe new data or we get new information, how does our probability distribution change? So, if we have a student and we want to know what's his probability of making an A in the class, right? So we have our prior distribution before the student enters the class. Now, when a student is in the class and he gets his first exam back, let's say he makes 90 on the first exam, then the distribution, posterior distribution, will update and excuse my chicken scratch here. This would be our posterior distribution because it would change as we receive new information. Now, here's an example of multivariant Gaussian, where we can see if we had an X here and we had a Y here, we would get our highest probability here. Now, speaking in terms of machine learning, these would just be features. So you would have, this would be feature one, feature two, and this will give you your probability of your class or whatever. Now, the beauty of this is that with multivariate Gaussian, we can make predictions using the mean and we can get the uncertainty using the variance. Now, let's say we have some random data. Now, our objective as machine learning and data science students is we want to create a model to fit this data. Now we can create a regression model or a classifier. Now, how do we approach creating a model for this data? Okay, now here are our random data points, and we have many different options for the model that we want to fit. We can do a linear regression, we can do a quadratic regression, which is more of a curved line. But wouldn't it be nice to have a level of uncertainty included in our models? Because the reality is uncertainty is intrinsic to every prediction. So let's say you wanted to take a road trip from Boca Raton to New York, right? You put this, you put a New York address in your GPS, and let's say it returns you an ETA of 30 hours. It takes you 30 hours to drive from Boca Raton to New York City. Now, how certain we are of this 30 hours? Is our prediction including weather delay, traffic delay, and these things in 30 hours worth of time? These things they're changing every hour. So there's a level of uncertainty that's involved in our predictions. This is the main goal of Gaussian process regression. How can we create a model that's going to give us a level of uncertainty for our predictions? Now, the Gaussian process is essentially the probability over your possible functions. So, the Gaussian process, the two parameters of the Gaussian process are the mean. Here's your mean here, and your covariance. Here's your covariance here. Now, one thing to note about this graph is that you can see these 2 points here, right? These 2 points, they have a tight covariance. Therefore, like the uncertainty is tight. Whereas when you see this point here, which is far away from this point here, then the covariance is wider. So your uncertainty, there's more uncertainty involved. Now the covariance of our Gaussian process is defined based on the kernel. We have many different kernels that we can choose from. We can choose a linear kernel, a periodic kernel for data with seasonality, a rational quadratic kernel. This, what we're looking at here, is a squared exponential kernel. This is the most commonly used kernel to define our covariance. There's two key parameters here. We have the L parameter in the denominator. This denotes the length scale, which determines the wiggles, the ripples, the wiggle room in our function. Um, and we also have the sigma, which determines the average distance from our function. And the further the distance is, the more uncertainty, basically. Now, with these two parameters, we have an infinite amount of numbers that we can choose from. Now, they often is from the research I've been doing. Gaussian process is basically looked at as a neural net with an infinite amount of nodes. Now, the fact that we can have an infinite amount of numbers that we can choose for our length scale and for our sigma is what give us these infinite properties. And we'll discuss this later in another slide. Okay, so I won't get into to the to the heavy math or the details of these other kernels, but I'll put them here so I can explain a point at the end of my presentation. Here are two other slides. Here are two other kernels. We have the periodic kernel, which is good for data with seasonality. Um, for example, if we want to track the retail sales that tend to peak at Christmas season, but they decline after the holidays. This is something that is this is a repetitive behavior every year. So it has this type of data we would use a periodic kernel. Now, if we had data that behaves more linear, then here is an example of the linear kernel. And just as with the exponential kernel, there are parameters here that can be set to an infinite amount of values, which, just to reiterate here, the Gaussian process behaves like a neural net with an infinite amount of nodes because these parameters can be set to an infinite amount of values. Now, the Gaussian process machine learning method can be used for classification, regression, and unsupervised learning. Here's an example of classification. We can see that the Gaussian process is definitely outperforming neural networks and random forests. Granted, we can see here we have high variance. So our model could be more susceptible to overfitting here. And we have high variance here as well to random forests. The neural network seems to be generalizing better because there is a balance between bias and variance here. It's not as uh, it's not as complex as your Gaussian process and your random forest. Now, in summation, the Gaussian process is just a probability distribution over possible functions. Now, what are the pros and the cons of the Gaussian process machine learning method? One big pro is that if you have knowledge of your data, you can choose whichever kernel you want to use that best represents your data. So you know if your data has seasonality in it, then you can use your periodic kernel to define your covariance. Now, if you know your data behaves more linearly, then you could use a linear kernel. So you just have all the freedom in the world to create your model. Now, another advantage that the Gaussian process has over other machine learning methods is that it provides uncertainty, a level of uncertainty. And as discussed before, uncertainty is intrinsic to every prediction model. Every prediction has uncertainty to it. What one of the main cons of Gaussian process? Well, unfortunately, it's computationally expensive. So if you have a data set of size n, then it, then the complexity would be big O n cubed with a storage demand of big O n squared. This is because the Gaussian process is a non-parametric method. So it has to take into account the entire data set with each prediction that it makes. Okay, this is pretty much the gist. This is the summation. This is the gist of my presentation. I hope this was very informative to you. If you want to learn more, you can feel free to YouTube. And once again, it's been a pleasure to take this class.